In this project, we are going to take the measurements of an existing tuna can and find the existing volume. We will then be using algebra and calculus, as well as graphing, to find the new measurements of an optimized tuna can, one that will hold more product, but without changing the surface area of the can. The idea is to maintain the surface area of the material being used, so as to keep the cost of production unchanged, but allowing the manufacturer of the tuna to add more product within the can if they wish to do so. For an existing tuna can, the measurements taken are: the height of the tuna can is 4.1 centimeters and the circumference is 27.2 centimeters. Let's find the radius of the tuna can using the circumference. The circumference equals 2 pi r. By putting the values, we get 27.2 equals 2 pi r. Dividing both sides by 2 pi, we get r equals 27.2 divided by 2 pi. This gives us a radius that is equal 4.329 centimeters. Now let's find the current volume of the tuna can. The volume is equal to pi multiplied by the radius squared multiplied by the height. Now put the values of the radius and height. The volume is equal to pi multiplied by 4.329 squared multiplied by 4.1. The volume is equal to 241.3858 centimeters cubed. Now let's find the surface area of the tuna can. The surface area is equal to 2 pi r squared, which is the area of the top and bottom areas of the bases of the tuna can, plus 2 pi rh, which is the lateral area of the can. We'll now substitute the values of r and h into the equation and calculate the desired surface area. The surface area is equal 117.749 plus 111.52. Adding these values, we get a surface area of 229.269 centimeters squared. Before we move to the next step, let's clean this up a little. Let's rewrite the surface area equation and use it to solve for the height h in terms of the radius r. Let's now substitute the values in the equation. 229.269 is equal to 2 pi r squared plus 2 pi rh. Subtract 2 pi r squared on both sides of the equation. We now have 229.269 minus 2 pi r squared equals 2 pi rh. Divide both sides by 2 pi r to solve for the height h. This all simplifies to 36.489 divided by r minus r equals h. We will now write the equation of the volume of the tuna can in terms of the radius r by substituting the equation found a little earlier. The volume is equal to pi r squared h. We'll now substitute the height equation into the equation of the volume and end up with an equation for v in terms of r only. The volume is now equal to pi r squared times 36.489 over r minus r. Expanding this expression and simplifying, we get v equals 36.489 pi r minus pi r cubed. Rewriting the equation in terms of x, we end up with v equals 36.489 pi x minus pi x cubed. Let's look at the graph of the volume equation, which you can get on your graphing display calculator or on Desmos.com. The graph has a maximum value at x equals 3.488 with a y value of 266.527. This means that with a radius of 3.488 centimeters, the volume of the tuna can be increased to 266.527 centimeters cubed. Now let's try and get these results algebraically using the equations we obtained earlier. We'll start by taking the derivative of our volume equation with respect to x. The derivative of v is v prime equals 36.489 pi minus 3 pi x squared. Setting v prime equals to 0 and solving for x, we get 36.489 pi minus 3 pi squared is equal to 0. Subtracting 36.489 pi on either side of the equation, we have negative 3 pi x squared is equal to minus 36.489 pi. We then divide both sides by negative 3 pi. We simplify this to x squared equals 12.163, square rooting both sides. X equals 3.488, which is precisely the same result we saw on the curve we graphed earlier. We now need to find the height of the optimized tuna can. In order to do so, we'll need to substitute the value of x found earlier, which is equal to 3.488 centimeters, into the equation to calculate this height. Recall that this value of x is the radius of the can. We had earlier obtained the equation for the height of the can, h, in terms of r. Let's write it out again and use it to substitute 3.488 in for x. H is equal to 36.489 over r minus r. Substituting 3.488 centimeters, for r we get h is equal to 36.489 divided by 3.488 minus 3.488. Simplifying, we get the height, which is equal to 6.9975 centimeters. Finally, we're now going to find the volume of the tuna can by substituting the same value of x, which is equal to 3.488, into the volume equation. V is equal to 36.489 pi x minus pi x cubed. The calculation proceeds as follows. V is equal to 36.489 pi multiplied by 3.488 minus pi times 3488 cubed. This yields a maximum volume of approximately 266.53 centimeters cubed. The height of the tuna can increased from 4.1 centimeters to 6.975 centimeters, and the radius of the tuna can decreased from 4.329 centimeters to 3.488 centimeters. Volume of the optimized can of tuna increased from 241.3858 centimeters cubed to 266.53 centimeters cubed, which can hold more tuna in comparison with original tuna can. When comparing this value of the volume to the original volume, we can get a value of how optimized the new tuna can is. We do this by dividing the old volume of the tuna can with the new volume and multiplying by 100 to get the result as a percentage. The result above shows a 90.57% optimized tuna can. This means that the existing tuna can with a volume equal to 90.57% of the optimized tuna can have its volume increased to hold more tuna whilst maintaining the same surface area so as to not increase the cost of material used in the production of the tuna can.